Okay. We were left off on this problem last time I was here Wednesday. And I figured out what I had done wrong. I had accidentally squared these ones in the law of cosines formula, and I didn't square these ones. So I just did the law of cosines wrong. So sorry. But you guys were right. So this is not 130. I just actually squared that. It was 2 root 65. So good catch.
How do you spell your name?
HR.
What? No.
My first name?
W.
Or my last name? My new last name?
Is it REYNOLDS?
Yep. Just like
the foil.
just like probably how you just. Yes, just like the foil. It's funny. Okay.
I don't know how to spell that.
So we were using law of cosines to solve this because we knew technically all 3 side lengths of these vectors. And so remember how we would like algebraically do this is we'd have to minus over the 18 first. Remember you can't combine these because this is my variable right here. So you minus over the 18 first. Then divide by this number. So you get the cosine of theta equals, and we should be getting a decimal that's in between -1 and 1 because I'm going to have to use inverse cosine. So we get, well, we have a negative divided by negative, so we get positive. And I get this decimal. 6, 1. Oh, I wrote 5 decimals. I went over 2. Usually I just do 4. 0 point, yeah. All right, so how would I solve for theta?
Plug it in.
Inverse cosine. And because I'm using law of cosines, and because for inverse cosine, my range of possible angles is from 0 to 180, I don't have to worry about getting a second solution. Okay, some of you made that mistake on that quiz. Did everybody need to take, I know you took that quiz to decide them. Anybody else took that quiz that needed to? You did? You did take it? I haven't looked at it.
I took mine.
You took yours? Okay, I think you were the only 3, right? Okay, thank you. So because we have inverse cosine, it will give you that angle that's in between 0 and 180, so you don't have to worry about the 2 solutions. So I got theta is about 60.2551. Now, to answer their question, it said find the angle between the 2 vectors. So what you guys really just found, or what we did together, was this one right here within this triangle, because I had my resultant vector of u and then minusing my v. But we talked about how those were congruent because vector v is going to have the same direction as the opposite of v, so they're technically parallel. They have the same slope, same direction. So those are like alternate interior angles, so it's going to be that same angle. Okay. Wasn't that fun?
Yes, it was.
All right, now we're getting into the doozy of vectors. So hopefully with a couple work days last week, you got like most or all of like the 6.3 homework done that you can do. We haven't done any of the word problems yet. And you kind of have like the applications. You kind of have just like the characteristics and algebra, I guess, maybe kind of down with vectors and kind of just starting to like visually understand them. And I know I have that worksheet where you do something like this. So now we're going to take what our knowledge about vectors and how we can use them and do them in application problems.
Miss Henchard, I never got that.
My name is Mrs. Rose.
I'm just kidding. I never got that.
You did it? Okay, I'll give you a copy. Oh. I'm bad. Is it not up there? Okay.
You forgot to hand them out on Wednesday.
Oh, you're right. Okay, who needs one?
Everybody needs one. Yeah, leave your hand.
You, why are these weird?
Why should I make copies of theirs?
I did make the copy.
Yeah, we did.
Wait, did I do it wrong?
They're just,
No,
why
you're
are
fine,
they
Jackson.
cut off? I think I
Why are
cut
they cut
off.
off?
You get it right. Back off.
You mean them?
I don't want the crap on me. Just cut off.
Oh no.
Yeah.
It's literally one thing.
Jackson.
Don't worry, I
get it
have
wrong.
nicer copies.
Alright, thank you. Okay.
Right.
Okay, alright, I see how it is.
Sorry, I'm like confused like this. It's not good. Not good. You have one? Okay. You had your hand up, right?
Jackson.
And Jackson, you didn't,
Stop, no.
you didn't hole punch them.
Jackson.
Jeez, Jack.
Yeah,
You're
yeah.
doing
How am I
everything
supposed to
wrong.
do my binders?
Do you want?
Jackson.
Who else needs one?
Jackson, no puts
Max, did you grab one?
Yeah, I have.
Jackson.
Bailey, you have one.
Stop it.
Okay.
You're so mean.
Sorry.
He probably did better.
Wow. So I get for trying to be nice for you and making copies.
I
You tell me I
appreciate
did a terrible job.
I appreciate your effort.
Did you like
E for effort.
Yes.
All right, so we've been talking, obviously like a long time. I went back to like that original when we first started talking about like vectors, like that original like reference of, vectors are quantities that involve magnitude and the direction. So if I were to like slide a brick, I would not only have to talk about like the distance, but also like which direction, 10 meters to the left or something like that. Or velocity, which is speed with direction, so positive or negative, like speed, miles per hour, something like that, is an example of like something that would be represented as a vector, because you have the magnitude, which is usually like length. It's just some type of like physical quantity, and then the direction, which we've been talking a lot about, can be represented like with our direction angles, or like slope too. But a lot of the times in the application problem, it's more like angles. So we talked about like the direction angles. And remember, the direction angles are measured counterclockwise from the positive part of the x-axis. So sometimes in the application problems, your direction angles might be given to you in like bearings, or like north 45 degrees east or something like that. So just keep in mind how your angles are given to you. You might have to figure out what the actual true like direction angle is of the vector. Okay, so I kind of broke this down in our two components for like application problems. So magnitude is sometimes length, but it's basically any like physical quantity. So it could also be, you could also represent the magnitude as like the velocity, or sometimes there's like force involved, just like a physical quantity. We can represent their magnitude. So force, velocity, and then the direction is usually given to us in some type of angles. So they might give you like the angles of force. Sometimes they're in bearings of velocity or motion. Sometimes like nautical miles. Well, I guess nautical miles would be like magnitude, but in the angles usually for ships are bearings. Okay, so there's two approaches we can do to solve these. I'm only going to do one problem where I do both approaches to show you. And then from there on out, I personally prefer to do them like analytically or like algebraically kind of. So you can do them by like using geometry, aka kind of like what we did here, is you can draw out the two vectors, and a lot of the times to get the resultant vector, you're gonna like add them together because you have two forces like acting like against each other. So sometimes it's like, okay, here's my airplane speed, but here's the speed of the wind. So it's the true like velocity of the airplane. So you got to counter in the force of like the airplane velocity, but then also encounter or like add in this speed of the wind. So a lot of times you're just like adding them together to get like a resultant vector. So you can like draw it out, kind of like what we've been doing for these ones too, like the ones where you're not given any true like numbers on them. Where we're at. These ones, you can draw it out and form a triangle, and then you can use geometry. So you can do right triangle trig, sometimes law of sines, law of cosines. But in order to do it geometrically, here you have to sketch your vectors like pretty accurately. So I'm just gonna put that here. I always sketch it out kind of like anyways, but I prefer to do it what we call like analytically or like algebraically. So basically, instead of like adding the vectors by like physically doing it on a coordinate plane, I put them in component form and I add them together because it's pretty easy to add vectors, right? We just add the vertical components and add the horizontal components together. I personally do that to find my resultant. And a lot of the times you'll have to like find the magnitude of the resultant vector or the direction. Somebody can kind of use like this little formula to figure out the new resultant vector and the magnitude in component form. Okay. So basically your two approaches, and we're just gonna do 1, 2, 3, 4. We're gonna do 5 application problems together. Yeah.
Why so many?
And it take a while, so I don't know if we'll get through all 5, but you know.
So how long are we gonna be on these notes?
Which one is the one I'm gonna do twice? Not the first one. The first one is the first one's pretty simple. Start simple. A bee is flying with a velocity of 22 feet per second at an angle of 6 degrees above the horizontal. Find the vertical and horizontal components of the velocity. Okay, so I'm just going to do a little sketch. So it says 22 feet per second at an angle of 6 degrees above the horizontal. It'll be pretty small right here. 6 degrees. So we're going to let this vector represent our velocity. I'll call it V1, or I'll call it just V. So the magnitude of this velocity is 22 feet per second. We're gonna write that. We'll call that the magnitude, and you can again let the magnitude represent really any like physical quantity. So a very common one is like if you're given velocity or force. So that's our magnitude, 22 feet per second. All right, so they just want us to find the vertical and horizontal components of the vector. There's 2 ways you could do this. So technically, like geometrically, what you could do is you could use right triangle trig to find this and this, because this would just be my horizontal component, and this would just be my vertical component of that right triangle right there. Or what I kind of prefer to do is like we could do this analytically, that I know this vector in component form is the magnitude, remember this little guy, times the cosine of the direction angle to get my horizontal component, sine of theta, the direction angle to get my vertical component. And that's really the same you're doing here when you're doing the right triangle trick. So whatever way you want to do it, okay? So that's kind of like geometrically, you could use right triangle trig. I'll write that over here. Your textbook, like I was looking at your homework problems and kind of how they do it, and they more do it analytically, like putting it in the component form. Okay, so to find the component form of this vector, we know the magnitude, which is represented by the velocity here, is just 22. So this represents magnitude. And I know what my direction angle is because they gave that to me. It's 6 degrees off the horizontal, and my direction angle is from the positive side of the x-axis. All right, and then here's one of like my algebraic characteristics with vectors. If I have 22 times that vector, I can just take 22 times my horizontal component and take that 22 times my vertical component. And I'm just going to give you these in decimals here because obviously 6 degrees is not something on our unit circle, so you just use your calculator. You get 21.8794 ... 2.2996 ... Okay, so again, if you would have done this using right triangle trig, you're getting this, which is our horizontal component. You would have gotten that 21.8 number. Then our vertical component is pretty small, which makes sense because this is a tiny angle to be that. You could have done right triangle trig as well. So to answer our question, horizontal component, I know in component form of vectors is this first number. So since we let these represent feet per second, this would also be in feet per second since that's what we defined our magnitude of our vector. And then the vertical component Now, a lot of the times the questions aren't just going to ask you for these two components. It's going to ask you for like the magnitude. It's going to ask you for the direction angle if it's maybe not given to you. And find the magnitude, you could again use right triangle trig. You could use Precalc. Or, well, I guess we know the magnitude of this one's 22. So
Is there any way we can abbreviate that?
abbreviate what component? Bless you.
Like the whole thing, can we just like
HC.
horizontal line going one way, horizontal line, and then just like comp,
You can do HC and BC if you want.
vertical line, and then just
Yeah, if you want to do HC and BC, that's fine. You could check your answer by using Precalc if you wanted to.
My calculator is dead.
Okay, so that's a pretty easy one. So a lot of times, you guys, how you're gonna like define what your vectors are for their like magnitudes. A lot of times, it's gonna be like velocity or like the force. Okay, let's try one with force. Actually, we're gonna try two with force. So this is the one I'm gonna do two ways. So you have to write small.
Okay.
Give you a warning. Unless you want to do
is
one
that long?
one way on your notes. I'm just doing it two ways, and this is the only time I'm gonna do it two ways. I'm gonna let you guys decide which way you want to do it.
Which way's longer?
I think I like the analytical.
I think analytical is actually probably like longer,
This one's analytical.
but I think it's just like a little bit easier to just put it in component form. It's like the same steps every time versus like geometrically you have to be super accurate with your sketches. You have to use law of cosines, which is kind of long, I guess, for most of them. I don't know. I'm curious to see what you guys will like the best. Come on.
Probably algebraically.
Okay, so we have two forces, 55 newtons and 200 newtons, pull on an object while maintaining an angle of 35 degrees between them. Find the direction and magnitude of the result. Okay, result meaning I'm going to have to add in these two forces together. So when you do these sketches, the easiest way, because you can kind of decide where you want to place your vectors, but the easiest way to do it is to do them in quadrant 1. So I have my force of 55 newtons. I'm going to put that one right on the x-axis here because it maintains an angle of 35 degrees between them. So I'm going to do this one right here. I'm going to call this, what did I call this one? I called this U. It's 55 newtons. There's one. That's my magnitude of that vector. And again, you can pretty much define those for whatever you decide, but a lot of the times you want to be given some type of velocity or force. And then my other one is 200 newtons, and it has an angle of 35 degrees between them. So kind of just somewhere, this one I'm going to call V, which is 200, and there's an angle of 35 degrees between them. Okay, let's do this geometrically first. Okay. So, to do this using geometry, you're just going to sketch the resultant vector, which is these two vectors added together. Okay, if you have both of these forces that are pulling an object, obviously they're combining their force to pull this object. So we just have to add them together to find their resultant. So you're going to sketch, and this is where you have to be accurate, U plus V. So remember how we do that. Actually, I'm gonna write it as V plus U because it's a little bit easier to do it that way. Obviously, it doesn't matter, but in this case, it's a little bit easier to take your vector V and add on U. Okay, so I'm just trying to be accurate. I'm taking my tail end of my vector V and I'm adding on U. So wherever that ends up, this vector right here would be V plus U. Agreed?
Agreed.
Okay. V plus U. This is how we do it using geometry.
Wait,
Yes.
if you did it U plus V, would it still be the
Yeah. You would just take this, add on this, see how to get to the same spot.
Oh.
Yep. Good question. And obviously, like, that makes sense too, because, u plus v is the same thing as v plus u, so it shouldn't matter what order you do it in. But that's why I said it's a little bit easier to visualize. I don't know, maybe not for you, but I would do it this way. But yes, you're right. Same spot. Okay. So now I can use law of cosines because I want to find the angle and direction of the resultant. No, sorry, the magnitude and the direction. Okay, here's what we know. We know these two are, since these are the same, these are parallel. Same direction. So I know if this angle right here is 35 degrees, what's this angle right here going to be? 35, yep.
Alternate interior angles.
Nice. Meaning this angle right here is how many degrees?
I'm sorry, I'm distracted right now.
Why?
145. 55.
Oh, down, Jackson.
Oh my god, I got a question.
Okay, so here's what we know in this triangle. Here's what we know in our triangle. We know this side length, so now just picture it as a triangle, kind of like ignore the vectors for a second. This side length is 200. What would the magnitude or the length of this vector be? 55, so we know this is 55. And we know their included angle. So I have a side angle side.
Stats.
I have a SAS. Do I know any like angle to their side ratios? No. So I can't use log. I don't know what this is. You guys know how to find that by doing it in component form. That's analytically. We'll do that in a second. But I have a side angle side set up here, so I can use law of cosines. But I can't use law of sines because I don't know either of these angles. But I know those sides. But I don't know this side, and that's what I'm trying to find. Okay, so here's how I would set up law of cosines. Okay, this side length, the magnitude of v plus u squared, this is law of cosines, is equal to the other two sides squared, so the magnitude of the other two sides squared, which I'll add in those numbers in a second. We add those together. Minus 2 times the length of the two sides, so times the magnitude of v, magnitude of u, times the cosine of the included angle. This time we know the angle, 145 degrees.
Wait, why
Oh.
isn't it 35?
Because 35 degrees is this angle right here, the one that's alternate interior angle. But 145 is the one that's inside this triangle.
What?
This angle is congruent to this one, alternate interior angles. Here's
Well,
the.
yeah, but aren't we?
We're trying to basically solve like this triangle right here. I'm gonna outline the triangle.
So we're trying to find v plus u.
Yep. See the triangle right here? So the included angle is 145 degrees.
Okay. So now,
Okay, I said I was gonna wait to plug in my stuff, but that's okay. So these ones I actually don't mind doing law of cosines because these are the ones where you just plug in all these numbers, right? It's a little bit easier to solve this algebraically. So the magnitude of v is 200 squared, and I'm okay. You don't have to write out like the law of cosines every time. This is just more for an example in our notes. Plus the magnitude or the length of vector u is 50 squared minus 2 times the magnitude is 200 of v times the magnitude of u, which is 55, times the cosine, we already said that, included angle, 145 degrees. Okay, so because all my numbers are on this side, remember, this is how you do law of cosines, right?
Yep.
Type this all in your calculator. Make sure you're in degree mode, and then you just square root it. I only wrote the final answer. This is what I got. So this would be the magnitude of v plus u, which that's what that represents.
is there labels and newtons?
It's newtons. Yep, I was just going to say that. It's newtons because that's what my other vectors were measured in, newtons. Okay, so there's the magnitude of my resultant. That was one thing I needed to find. Okay. So now to find the direction. So remember how our direction angles are measured? It's from the positive side of the x-axis to that. So here, this is technically my direction angle. So to do this like using geometry, I then found this little angle right here in my triangle. And now I can use law of sines because now I know what this side length is and its opposite angle ratio. And then I can use this one. So I got to find that. And then I could just take 35 minus that little angle to get the direction angle. Everybody see that? Because that's what the direction angle is. It's this one, not talking about like the angle between any of these, the direction angle from the positive x-axis to where the vector ends up. Okay, so to find this one, here's how I set it up. I did my 55 over the sine of that little angle. I just call it x, law of sines. And then I could do this 24, sorry, not 24, 247. What we got for u plus v divided by the sine of what?
145.
145, good. Okay, we cross multiply. You guys all know how to do law of sines. You guys killed it on the quiz. Just keep in mind here, you're going to divide both sides by this number. I'll do this in my calculator in a second. And you should get x, which we're going to have to use inverse sign because I'm trying to find the angle. You should get x to be about 7.3355. Okay, let me get my calculator up here. I'll do it with you guys. So let me go ahead and get that. Let's get that magnitude, that exact value in my calculator here. So once I, like I said, just kind of plug and chug in that law of cosines. So minus 2 times 200. Ooh, I don't know if I'm in degree mode.
Your gradient.
Rad. Good thing I thought of that. Okay. So once I get this, I'll have to square root it. Ooh, I typed in wrong. I didn't catch my 4. Okay, there.
Uh-oh. Rihanna.
Oh. There you go. There's that magnitude of the resultant vector. Okay, so now I got to do 55 sine of 145 degrees divided by that number. Okay, this is what my sine of x equals. So I divide both sides by that number. So the sine of x equals that decimal. So to get x inverse sine. Okay. Good with that? Now remember, that's not my answer. To find the actual direction angle, which I put theta, we'd have to do that 35 degrees minus x. So 27.6444 would be the direction of that resultant vector. Okay, so that wasn't too bad. We used basically like, I don't know, it's obviously not geometry, but law of cosines to solve that. If that makes sense to you and you're like, okay, I like that visual, and there's some in your homework where they're like this, and I tell you, like, you have to use law of cosines to do it as just like practice. But if that made sense to you and you like that, that's great. Now I'm going to do it like analytically just by using like the component form, kind of just like some algebra. Okay. So, second way. Basically, we're going to go through the same exact steps, but instead of adding the vectors by drawing it, we're just going to do it by putting them in component form and then finding the magnitude by square rooting the horizontal component squared and the vertical component squared because it's really you're just doing pi thing. Okay. So let's put our vectors in component form. U is easy because I placed it right on my x-axis. What's the horizontal component of U? 55. What's the vertical component?
0.
0. Okay, there's that in component form. Vector V, I'm going to have to do a little bit more work. I'm going to have to use that like little formula where I need to take the magnitude times the cosine of the direction angle, which is 35 degrees for the horizontal component, and then the sine of 35 degrees. Let's just go ahead and plug in the magnitude, actually. We don't need to write out the formula, sorry. The magnitude is 200. Okay. This is one that's not on our unit circle, so decimals are okay. I got that. For the horizontal component. You know, make sure your answers like make sense. If you drew this in quadrant 1, you should get positive directions for your horizontal and vertical components. Positive like values. Okay. There's vector V in component form. So then find the resultant. How do we add two vectors? How do we add two vectors together? We just add together their horizontal components, right? We talked about this visually. You're just taking this horizontal component and you're adding on this horizontal component. So you just take 55 plus that, which is 218.8304. Okay, and then you add the vertical components as well. Obviously, we didn't add anything extra on there. So 114. And that would give you the component form of that resultant vector. Here's the horizontal, here's the vertical. So then how do we find the magnitude when we're in component form? You just square root, yep. Horizontal component plus vertical component, because what you're really doing is pi thing there. And I'll draw a picture in a minute here. Okay, I'm not going to write the whole decimal, I'm just going to do 0.8. And you get that same answer that we got up there. It's the magnitude of the resultant. Okay. All right, so let me just draw you a quick sketch, and it helps with finding the next one. So basically, I know U plus V. I know this horizontal component is 218. Vertical component is 114. So if I were to draw that vector, this U plus V, I know this distance is that 218 number. I know this distance is that 114 number. So find that magnitude, you're just basically doing the pi thing. This squared plus this squared, and then you square root that. All right, now we got to find this angle. So find that angle, and you can do this every time, like analytically, after you find it in component form, you just take the tangent of the angle is equal to the vertical component, opposite over adjacent, divided by horizontal component. So I guess this is kind of a little version of right triangle trig, if you will. But that would work every time after you find the resultant vector. Well, I should say you should be a little cautious with what quadrant it's in, because maybe your resultant vector ends up being over here, and that would only give you like the reference angle. So you might have to be like a little cautious with that, but you're going to use tangent in almost all of these after you're given those components. Okay, anyways, you do that inverse, you get that same angle. So I kind of prefer this way because, like I said, it's very procedural. I'm a pretty procedural person. Put them in component form, add them together. You want to sketch a picture, you can. Find the magnitude using our little like formulas that we talked about, and you can find the angle by using like tangent. Okay, or you can draw it out. The only issue with this is like, this can be different every time. Maybe you don't know this angle, and that's okay. You can still use log cosine to find it if you know a side-side situation or something like that. All right, kind of makes sense.
Sure.
Any questions?
Wait, is there a scenario where we're gonna have to do one over the other?
No,
Besides you just saying to do one?
not on application problems. No. The only one would be like this one says like use the log cosines to find the angle between the two vectors. Technically, we could have done that same process of like, oh, can you let Mr. Orchin, please? We could have done that same process of
What's your password?
doing a component form. I think some of them already have it, yeah,
Okay.
but perfect.
Because they'll be here for first time.
Got it. Thank you. Oh, what about the kids who are testing?
I'll talk to Miss Nick.
Okay, I sent her a
She usually
message.
just takes care of it.
Okay, I thought they'd probably just make up their testing.
Miss
Yeah,
Rose,
right.
can you make it so you miss the whole day, please?
Like, just do testing.
You beat me last time.
You probably don't know.
What's all?
It's just Tyson, yeah. Well, and a couple of sophomores now too.
All over the place.
So
This
Yeah.
is too smart for those tests anyways.
Did she die or?
yeah. Okay.
We don't
I
have
didn't
time.
want to say it out loud.
We do not have time.
Okay, so-
We won't finish this. So okay,
So
we'll
we
stop.
should just, yeah.
We'll stop.
Saving grace.
We'll stop recording.
Recorded.
Jeez, talk about.
I mean, I wanted to, but at the same time, I want to put an effort into it.
Leave you last time.
I did.